So some of you may be wondering what PCB Piezotronics has to do with the Modal shop. Well, put as succinctly as possible, the Lally family founded PCB Piezotronics in Buffalo, New York. One of their sons, Mike Lally, founded the Modal shop in Cincinnati, Ohio. The Modal shop integrates PCB Piezotronics sensor solutions into its products and also rents instrumentation that's made at PCB. This is an aerial shot of PCB, and I spent the first 10 years of my career at this facility, and it's grown tremendously in that time, in the 15 years overall that I've been with the company. When I first started, it was just the building at the top of that aerial shot, and now that second building has been added. That's a full machine shop. We used to have the machine shop in the main building, and now the machine shop is its own separate facility that runs 3 shifts. And there's also a manufacturing facility in North Carolina, which is not pictured. So PCB is the largest manufacturer of piezoelectric vibration sensors in the world, and they control the process from start to finish, raw materials to sensors.
And the Modal shop, on the other hand, is we're a system integrator, and we do some manufacturing in Cincinnati, Ohio. We're about 70 or 75 people here in Cincinnati, and we're the systems and calibration division of PCB, to use a familiar term. We integrate laboratory calibration systems. We rather than doing manufacturing and machining a lot of metal, we have that ability in Depew, New York for us. And we do in the system integration, we buy Windows PCs, we buy PCB sensors and signal conditioners and NI data acquisition cards and from other reliable suppliers to integrate systems and build software around them. And in addition, as Mike mentioned, we do rental services of all this equipment, and the systems themselves that we build software around. We provide ongoing services and support on site and training events on customer sites also. So a little bit about me. My name, as I mentioned, is Mike Dillon. I have a mechanical engineering degree from the University of Cincinnati. I've been in the PCB in the company for 10 years at the beginning of my career, took a break for a while, came back 7 years ago, and I'm the calibration system team leader at the Modal shop, where we do product management and applications engineering before and after the sale. I got hooked on sensors in year 3 of my years at UC, and after I graduated from UC, my fun fact, as the marketing department asked me to do, is I was at the 1999 UC Bearcat versus Wisconsin football game, which was the greatest upset in the history of UC Bearcat football.
And I've spent 16 years with PCB, and I was at the greatest comeback in NFL history. So was everyone else who you've ever met from the city of Buffalo, New York. But in 1993, the Buffalo Bills were trailing the Houston Oilers 35-3 with 9 minutes left in the third quarter and managed to win the game. And the only reason I was there was because my father wanted to see the game so bad, and it was blacked out on local television. So we had to go. It was bitter cold. Half the stadium left. But if you ask anyone from Buffalo, I've never met anyone who has admitted to leaving that game. Otherwise, I do a bunch of vibration stuff. So we can move on.
Great. Did they tear down goalposts at that game?
They did not. Did they tear down the goalposts at your game?
The game that they tore, the crowd stormed the field as they do in a great home win. And the thing of it was, there were like 2,000 people in the stands at that game. It was a beautiful day, but UC football wasn't as popular at the time, and it was just a unique event to be on the field when like 200 people went down on the field to be with the team, and they actually tore down the goalposts. I wasn't a part of that, but I was right. I was nearby when they came down. It was kind of it was easy to avoid the danger of it, so it was a unique experience.
So you supervised it?
No, I kind of I watched it as it came down, and it was just a really unique experience. So
Between PCB and the Modal Shop and Accumetrics and Larson Davis, we have a lot of solutions for the power gen market. Vibration monitoring, of course, is a core technology. We also have systems that detect current arcs on brushless generators that cause damage to that equipment out of our Accumetrics group. Proximity probe troubleshooting, even though we don't make proximity probes, we have a lot of content on how to troubleshoot proximity probes and products to do so. Combustion dynamics is another application we'll get into today. Noise and sound exposure measurement, industrial hygiene, and of course, slow speed monitoring equipment for hydropower.
that's the power gen side that Mike knows a great deal about. And from the Modal Shop side, like I said, we're systems and services for PCB products. And the systems that we provide are the ones we'll talk about here today are calibration systems. One is our 9155 calibration system that calibrates a large number of PCB sensors, and the portable vibration calibrator that Mike Scott is the product manager of. And of course, on the services side, we perform accredited ISO 17025 recal services. And a big part of our business, which is really helpful for a lot of people, is we rent all of this instrumentation to customers. So the question might be, what can go wrong with my piezoelectric sensor, Mike?
Well, some of the ways that piezoelectric transducers fail are due to damaged crystals or debonded crystals or depolarization. Most industrial instrumentation has a ceramic sensing element, which is not naturally piezoelectric. So it's artificially polarized. And over the course of time, the depolarization of the sensing element can cause sensitivity shift. You can also have a loss of hermeticity or broken wiring or a loosened preload. And I'd like to point out that on gas turbine sensors, all of them are high temp charge mode sensors. So they don't have a bias voltage. So an ICP sensor has a bias voltage, something you'd find on like an electric motor has a bias voltage, which is a nice red light, green light for your signal conditioning to show that the sensor is working. But when charge accelerometers completely die, they just fail to produce an output. There's no bias voltage. Usually you can catch it because you'll have an unusually low vibration or pressure level. But if you normally have noise in your signals, that can be missed. Or if you normally run really smooth and expect a low vibration level, it could be missed, but you'll probably catch it if it flat out dies.
Yeah, that's a trade-off with these high temp applications, right, Mike? It's the nice red light, green light of ICP is sacrificed for the high temp.
Yeah, the electronics just can't survive the high temperature application. The electronics will give you that nice red light, green light. So why calibrate combustion pressure sensors? Well, there are the obvious reasons shown on the slide. Combustion dynamic system optimizes the air-fuel mixture on a gas turbine, which has tremendous environmental impact, as well as contributes to the prevention of catastrophic failure. I'd like to point out something that might not be as obvious. Over the course of my career, I've watched this application evolve. Vibration is a little bit older application, but this one's relatively new. And it started with infinite coil, which is the picture at the top of the slide. And as with the sensors located pretty far from the heat of the gas turbine, and as the sensors got closer, they were developed, they could withstand higher temperatures, and the frequency response got better. And now the pressure diaphragm is right inside the combustor on most designs, and we have sensors able to withstand these extreme high temperatures, as you see on the slide, or the picture at the very bottom of the slide with the diaphragm of the transducer right there inside the combustor. The one thing that has not evolved is calibration. Some of these pressure sensor manufacturers, not all of them, cannot calibrate at the relevant amplitudes for the application. So often when you install the transducer, it was not specifically tested for a real combustion dynamics application. And also the sensitivity tolerances are very high, 20%, maybe even higher. So there's a wide range of acceptable outputs. The onus is on the end user to make sure their instrumentation produces reliable, consistent data, and the best way to do that is by calibrating. All right, still staying on the soapbox here. Why calibrate accelerometers? Well, I can recite the same reasons on the slide, but I'd rather talk about this minivan. And I don't know what kind of minivan that is, some generic picture. It's not my minivan. But there's an amazing vehicle evolution happening now regarding safety. It won't be long until cars can completely avoid an accident. Right now, I think they just slow you down if you're about to rear end. They always say you can't rely on this system to avoid an accident. You have to still participate in driving, right? I mean, I haven't gotten in a car yet that just flat out prevents the accident if you're about to rear end someone. But it starts to slow you down and then you slam on the brakes. The thing is, this technology is completely useless if you're driving on bald tires. The tires are the only part of the car that touches the road, hopefully, unless you drive like my wife. Your sensors, pressure or vibration, are the only part, don't tell her I said that, are the only part of the monitoring system in contact with the machinery. So you can have the most sophisticated monitoring system on the planet, and if the sensors produce incorrect signals, it cannot protect you. And the analogy, in this analogy, by the way, Mike, being from Ohio, state governments are like the standards, right? And vibration is New York State, which is my home state. And combustion pressure is like this state, which is Ohio. Vibration has all these standards like API 670 that encourage you to calibrate. And New York has car inspection that prevents you from driving on bald tires. My dad was an auto mechanic. He did the car inspections. Meanwhile, combustion pressure has no standards just yet, just like Ohio has no standards for the vehicle that you drive. And that's why every time it rains, it takes me twice as long to get home, because it never fails. Some guy in a 1984 Stanza with a piece of snow fence for a door and a duct tape plastic bag for the rear windshield has spun out on the interstate and blocked 2 lanes of traffic because there's no car inspection here in Ohio, and that's just like combustion dynamics. It's a wild west out here.
Wow.
All right, I'm done. I'm off my soapbox.
Wow. That's
very upset about the time I spend in the car.
On behalf of the state of Ohio, I apologize for your delayed commute. I don't think it's just isolated to the state of Ohio, though. But it's a great metaphor. Thanks, Mike.
It's not.
So, what do we do when we calibrate accelerometers and pressure sensors? So, there are two sets of two calibration events in the life of a sensor. The original calibration of the sensor, where what we do on the original calibration, the purpose of it is to make sure that PCB meets the promise it makes on PCB.com, which you see there on the right, where there's a combustion dynamics pressure sensor, and PCB specifies its characteristics in the lower right-hand corner. So PCB makes that commitment on a product specification sheet, and what we do in final calibration is make sure the sensor conforms to that. It's a 100% acceptance test at the end of the line. And the recalibration is the other event that we have. And the purpose of it is to identify sensors that are damaged and need to be replaced, and possibly avoid the replacement of a sensor. When you localize, if you have a bad channel of the data acquisition, you can avoid that cost by localizing it to the sensor, quite often a cable or something else, right? That's what we're doing in the recalibration event for the sensor. So what does the calibration verify? What kind of data are we taking? And it's we talk a little bit. It varies a little bit here. Common ones are the sensitivity for an accelerometer, the frequency response, the amplitude linearity, the mounted resonant frequency of a sensor, of the accelerometer. Pressure sensors, same thing, sensitivity, linearity. Another one that we do at the original factory calibration quite often is insulation resistance. That can be a valuable indicator of the sensor health, or its its future health if the sensor installation drops. That's usually an indicator that the hermeticity is lost, right, Mike? Okay,
Yeah.
so these sensing elements in here need to be sealed from all any kind of weather conditions, moisture, any kind of toxic materials, and they need to be kept dry and clean. And we do that with a hermetic seal around all the connectors and the sensing element. So that's another measurement we make at the original calibration. So what do these mean? The frequency response, I think we know the sensitivity. The thing about sensitivity is I'm a mechanical engineer, and the take I always say is the problem with our sensors is that they have an electrical output, and that's not really usable unless you know the sensitivity in if you get a picocoulomb output. If you want it to be in picocoulomb, if you want to know the G level, you need to know the sensitivity. And what we see here, that's a sensitivity in picocoulombs per G or picocoulomb per PSI that's measured at a reference frequency. 100 hertz in my language, that's 60 cycles per minute, right, Mike? So you'll see the frequency expressed in different terms, either in units of hertz or CPM. And then the other thing we do is we do a sensitivity measurement sweep across the frequency range to make sure that the sensor, the accelerometer is within tolerances for either plus or minus 5% deviation or a 10% deviation or a 3 dB limitation relative to that reference sensitivity. And you'll see those three different, we have two in this spec sheet from PCB, we have a 5% range and a 10% range. And you'll see on those two ranges, the 10% range is always a little bit further. And that's because it's that 10% deviation range is an expanded frequency range compared to the 5%. And then the mounted resonant frequency, we measure that also quite often. And that's a rundown of the most common accelerometer calibration data. On the pressure sensor side, it's the common ones are amplitude linearity and again sensitivity, of course. And what you see here is a CalCERT, data from a CalCERT of a pressure sensor. And we're doing an amplitude linearity sweep where we're testing at 2, 4, 6, 8, 800 and 1,000 PSI, and we measure the voltage output. And what we'll do is the actual data we take is not exactly at 200 PSI, but we take 5 averages and average the reference level, and we average the output level, and we calculate a sensitivity based on that. This one happens to be in millivolts. And then for all that data, we draw a best fit straight line through all of it, and we measure the outlier data point, which is highlighted here in red. And that's the worst case nonlinearity of the sensor. In this case, 0.71%. And we use that to compare against the spec sheet, which is typically a 1%. It could be more, it could be a 1 to 2% nonlinearity allowance. Those are the two main criteria for a pressure sensor calibration. And just looking at the CalCERTs between the two, the thing we're looking for on our accelerometer sweeps is we want a flat line across the frequency spectrum. And on pressure sensors, we want a linear line, no bend in the curve. That's really what we're looking for. So moving on, the two types of calibrations we do look like this. On the accelerometer side, we have a vibration shaker, which creates vibration in we assume a perfectly vertical direction. And on top, there's a stack of instrumentation here, which has the test accelerometer sitting on top, the reference accelerometer below it, and they move in a back-to-back configuration to get a common vibration level between the two. And then we compare the voltage output or the electrical output of the two, knowing the precise sensitivity of the reference accelerometer to calibrate the test sensor. On the other side, on the pressure calibration, we're doing a different technique. It's called a volume expansion. We call it a step rise. And in this, we have a large pressure tank, which we call the large volume over here. It is, and attached to it, we have a static pressure gauge, which we've calibrated very precisely. And it's in a large volume. It's like 5 gallons in this unit we'll see later. And we expand that. We just open a valve into a very small volume over here on the right, where we have a sensor under test mounted. And that causes a drop in measured pressure of the static gauge, but the drop is really, really low, and it's below our ability to measure the difference. It's an incredibly small drop. And then we have a very controlled, very precise rise in pressure with a dynamic input to the sensor as we're measuring dynamic pressure events with it. And then we measure the output of the sensor under test. And so that's the kind of the schematic of the two methods. And from there, we'll go into the what these things look like, right? What do these shakers look like? And on the right over here, we have 3 different kinds of shakers we offer at the Modal shop. A precision air bearing shaker, which is used in our 9155 laboratory grade systems. And we'll talk about its specs later. And then the portable vibration calibrator, which Mike is the champion of and the expert on in industrial calibration. And we also have a high payload shaker for those sensors for those accelerometers that cannot be calibrated by the other 2. So we'll do a rundown now of the specs, a little bit of what they look like. You want to take a run at the PVC, Mike?
Yeah, so portable vibration calibrator, 800-gram max payload, 5 to 10 kilohertz frequency range, plus or minus 3% precision. Not the most accurate calibrator that is on the market or that we have to offer, but it's portable. So a lot of plants will use this device to loop check the vibration monitoring system and test alarms, which you'll see in a video that's upcoming in the presentation. So we'll hold off on what it really does until we get to the video.
That's one thing. If you're thinking about accelerometers today, it's really interesting. You should check out all the videos Mike has put up with the portable vibration calibrator. He's developed applications to check alarms, crack probes, any number of things. I can't list them all. Mike's
I have 3 hours of video content.
I'm not up for 3 hours.
If you're really bored, you can knock it all out in one afternoon.
All right. The air bearing shaker from PCB and the Modal shop has a 500-gram max payload. Not quite as much as the PVC. Extended frequency range it's really used for test and measurement sensors, but it's part of a larger system that will deliver plus or minus 1% measurement uncertainty, which is a slightly different value, a slightly different unit of precision than the accuracy that Mike states in the PVC. And then once you get up to 15 kilohertz, it's roughly plus or minus 2% measurement uncertainty for a coverage factor of 2. But we're not going to go into all the statistics and how the statistics are done to get those values. But that's part of our larger laboratory system. And another shaker that we have is a flexure-based shaker, and it is the H75 series. It has a 3 kilogram max payload, 2 kilohertz frequency range. This is for really high payload sensors. And it has a uncertainty of plus or minus 2.5% up to 2 kilohertz. And we can run it up to 10 kilohertz, but we haven't quantified the measurement uncertainty due to some of the resonant frequencies and the modes inside the shaker. So a little bit, now we'll do a look at one of these applications Mike has developed.
Yeah, so this is a video, and here's a look at how the portable calibrator is actually used. I think you got to turn off your laser pointer there to play the video. But on the bottom is the calibrator, and in the bluish hue is the known vibration values. And then we have a little alarm module at the top. Keep your eye on the alert and alarm lights at the top right and the display on the alarm module as we fire up this video. The first alert is going to occur at a 1/2 inch per second peak. So as soon as I creep over that number on the calibrator and then the vibe alarm catches up, we have a 3-second time delay, and boom, you see the alert light trigger. Now we'll do the same thing for the vibration shutdown alarm, which is at 1 inch per second. The portable calibrator, again, the output there is in blue. And then once the vibe alarm catches up, we have the 3-second time delay, and you see the alarm trigger. And in a nutshell, that's the primary application for the portable vibration calibrator. It's quite often not so much creating calibration certificates as it is just verifying vibration, alert, and alarm shutdown values and shutdown logic.
Right. I'm just catching up with you here, Mike. I'd like to point out the thing I'm seeing is the actual accelerometer is mounted on the lower left. This is the accelerometer that's connected to the vibe alarm, and it's the readout for this accelerometer is the green, and the readout for the reference accelerometer buried inside this unit in the shaker is in the blue.
Yeah, and you see a slight difference there. The vibe alarm's anticipating a 100 millivolt per G transducer, and perhaps the output of that transducer was 99.5 or whatever it works out to be. And that'll be the case with anything you test. Proximity probes, the nominal sensitivity is 200 millivolts per mil. So the monitoring system is programmed for 200 millivolts per mil, but the actual might be, 202 or 203. So, it's very, sometimes you get a perfect situation where the numbers are exact, but there's always a little error. Usually there's a little error there between the known vibration level and the actual measured value.
And similarly, we have this is just a video of the air bearing shaker working. It's working at a fairly low frequency right here. It shows the vertical motion, and similarly, the reference accelerometer is buried inside of the shaker, and you see the accelerometer we're testing on top. Then we're not going to do a whole dissertation on the software operation for it because we're just not doing a 9155 webinar here. But the 9155 sensor calibration system, at the core of it, it's the 9155 software, and we use it to calibrate high frequency of vibration, shock acceleration, visual outputs or meter calibrations. We do acoustic microphones. It has a low frequency vibration option. And the next one we'll talk about here is the dynamic pressure option, which reproduces the factory technique used on these combustion dynamic sensors. The 9155 software ties everything together by automating the test setup, the data acquisition, and the data management. So it's another level of complexity and another level of automation and tying the whole system. But it's interesting, these pressure cal systems for combustion dynamic sensors, we can calibrate them with two different calibrators. They have different max pressures and they overlap. So the 9903 series on the left that's actually a kind of a piece of furniture that goes on a bench top, and you'll see this oxygen tank in the front. Overall, this system is about 2.5 feet wide by 3 feet deep and about 2.5 feet tall. And it'll sit on a bench top next to a data acquisition computer and signal conditioning to collect data for a pressure sensor. On the other hand, the 907 series is 1,000 psi, has a max pressure level of 1,000 psi, and it also sits on a bench top, sits about 3.5 feet tall. And they measure using what we call a step input that I described earlier, and it calculates sensitivity. The software enables calculation of sensitivity, nonlinearity in an automated fashion. So this is the technique we talked about, the large volume. So for example, this large volume, what it looks like, I'm going to jump back a slide. The large volume in the case of the 903 is encased in a pressure vessel in the back of it. It's not visible here. And the large volume in the case of the 907 is the mid frame, about 2/3 of the way up. I'll get my laser pointer out here. Is in this area. And you'll see how small of a volume we expand that into later. And you'll see it on the 903 too. So here's a video. We show the data acquisition of the 903 series. This is a little bit of an older model with a red tank on it. Just so you know, this red tank is not the large volume that we discussed that I mentioned before. It's actually a mechanical filter that we use. And you see that the operator here is opening the valve with the flick of the thumb. And each time he does, he collects another data point that are collected here, and it's collected in data table. And then we fast forward to a higher pressure level, and you can see this the line of data that we discussed, the diagonal line, and he's collecting that data with the sensor and test is, as I say right here. And it's a similar process on the 907. So this is a close-up of the 907 that will show, we'll open the cases up on the top of it. And we highlight that's the sensor under test location. And then we'll move forward to the actual data acquisition, where our operator is opening the valve by popping slamming the weight down to collect more data. See there, he slides that mass down the valve stem, and he collects data over and over again like before. The other thing you'll notice is this in the time domain data up here, the step rise data, it's a lot faster. That's just not scaling. This unit has a rise time of like 30 to 50 microseconds compared to the millisecond durations that are in the 903. But very similar process. And then the data, a little slow down the data acquisition. This is the rise in pressure in the blue curve that we saw. This is the gas expanding into the small volume and hitting the diaphragm of the sensor under test. And we collect the data, the statistical data down here to show the linear relationship. And a little bit more, this could be, it looks like a complex software interface, but we do things in the software, and primarily we measure the rise time, which is a good operator. The operator checks his data, because if he has a bad rise time, he can detect it in the software, and we can reject that data in the software in case there's been an operator error. And the rise time is just the time it takes for the signal to get from the 10% full scale value to up here at the 90% full scale value. So we take this data and we we compile it into a CalCERT, and this is the various components of it. Again, I'm beating to death here the diagonal nature of the curve. We have a data table over here at the data points that we collected up through 20 psi, and we calculate the sensitivity in picocoulombs for psi, the linearity as a percentage, and the uncertainty, which is you'll see that on CalCERTs. That's not a characteristic of the sensor. That's a characteristic of the calibration system, and that uncertainty is determined through statistics and peer review and an auditor review from A2LA that accredits this calibration in the U.S., and they're a member of the ILAC association worldwide that maintains consistent traceability and accreditation for all the countries in the world.
Well, let me ask you something, Mike. Can you go back one?
Okay.
Can you do that plot from 1 to 5?
Yes, we can. Good point. Absolutely. That's the characteristic. That's the ability of the 903 series calibrator. We have a low pressure level of 1 psi, and then it can be configured to stop at 10 psi or go up to 150.
What do you think? I mean, combustion dynamics is kind of down there in the 1 to 5. If you were doing that type of application, would you run it to the full scale, which is usually 20, or would you stop at 5, or it's completely up to the end user?
It's up to the end user.
Yeah.
And
no standard or anything. Like I talked about.
Well, a good standard is repeating what the manufacturer does.
Yeah.
And this is the manufacturer technique at PCB. And you can easily find on your original calibration cert, or you can call an application engineer, your local field application engineer from PCB, and they can get you the information on how to reproduce that factory calibration. And hopefully you'll end up talking to us here at the mobile shop.
So this is an accelerometer frequency response sweep, and you can see the sensitivity of this transducer at the top of the screen. It was 100 millivolts per G. This sweep is done in cycles per minute, so 1 hertz is 1 cycle per second. So 1 hertz is equivalent to 60 CPM, and 100 hertz is 6,000 CPM. So that's why the sensitivity is written there at 6,000 CPM. But the main takeaway from this graph is that we're confirming the accuracy of the accelerometer throughout the frequency range. So, accelerometers are used to pick up vibration at 1 and 2 times running speed, as well as gear mesh, inner and outer race bearing fault frequencies. So it's important that we test the full range of the transducer to ensure the accuracy for all of those faults. So no matter what type of faults the machine is producing or what type of faults you're looking for, you know that you're getting an accurate signal from the accelerometer. And you can see on the data at the bottom there, the low end frequency is 600 cycles per minute, and the high end is 360,000. And the maximum deviation that we saw from 100 millivolts per G was 3.1% down. So that's about 97 millivolts per G at 300,000 cycles per minute.
So this frequency response data, Mike, PC do that for the fun of it, right? There's a reason.
It's not much fun.
Yeah, exactly. Good. Yeah, exactly. And there's no fun in it, and there's little fun in it, but they do it, right? So there's a reason for that. And
yeah, on a precision picture an accelerometer that you're using with a portable vibration analyzer, you're going to rely on this accelerometer to take thousands of data points. You're going to use it every day. You're going to use it on a variety of pieces of machinery. You might walk up to an electric motor or a pump or what have you. And, it's important that accelerometer is tested throughout the frequency range so that you don't have any areas of localized resonance. It might produce a false alarm, really. Might, a sensor that is producing an elevated signal at high frequency can produce a false alarm, which is almost as bad as a real alarm. So, it's very important that you do the sweep, and all of PCB's precision industrial vibration sensors come with a full frequency response sweep. And then this is a single point calibration. This is not recommended per the ISO 16063 Part 21 standard, but you do see it in the industrial market on lower cost accelerometers. And just like anything else, you get what you pay for in vibration instrumentation as well. So there's a lot of companies that'll just offer a single point calibration and offer a very low price for their transducers. And the downside to this is we do not know if the sensor is accurate at other frequencies besides 6,000 CPM or 100 hertz. So we have no idea. Go ahead, Mike.
This looks great, though, if you had a sensor and you only wanted to measure at 6,000 CPM.
Yeah.
Is that common in industrial measurements?
No.
That's what I thought.
It's unusual to only be interested in that specific frequency. So we have no idea if the sensor is accurate in the high frequency range. If I was using it for gear mesh, I can't tell from this calibration report if it's really accurate for that application. And most turbine OEMs use sensors that are only calibrated at one frequency. So sometimes it's 120 hertz instead of 100, but you only get that one data point. So it's kind of interesting that those transducers are mounted permanently on the gas turbine, and they're really your last line of defense for a vibration issue, and they're only calibrated at one point, which doesn't follow the ISO standard. And so again, the onus is really on the end user here to make sure that the instrumentation is working correctly. Ultimately, when it comes to downtime, when it comes to catastrophic failure, it's the end user that is in charge of making sure that doesn't happen.
Right. Great point, Mike. Thank you. And that pretty much, we're 5 minutes over in our projected time to finish. So we're going to wrap it up. Looking forward to the future webinars in this series. This is January 21st. This is your webinar, right, Mike?
I am up next, January 21st. How to turn your smartphone into a vibration analyzer. New technology in the industrial vibration, or in the vibration market in general. You can connect a digital accelerometer directly to your smartphone, and you're really only limited by the app that you buy. I mean, there's a variety of apps out there that give you a basic vibration measurement, or You can go with an app that I have on my phone that really gives you everything that you would get with a portable vibration analyzer. You can choose your window, you can choose your resolution, frequency, anything that you can do with a portable vibration analyzer, almost anything you can do on this app. So it's pretty neat. It's breaking down some of the barriers to starting a vibration monitoring program, or at least taking some vibration data by using your phone as the piece of instrumentation that's going to do data acquisition.
That sounds like a great app.
It's fun, yeah.
Yeah. That's a long ways from when we started in this business, when it was a big Unix mainframe computer that you needed to have all that stuff. This is all on a smartphone. That's amazing. So that's what we're looking forward to. That wraps it up for today. Thanks, everybody.